Right, year 11, hopefully that is a little bit clearer. I'm just going to move it so that you can see the full paper. That bit better?
Yeah, that's okay now.
Lovely. Sorry about that, guys. There we go. Okay, so very quickly, it's over to Mr. Addy and then Mr. Clee, who are going to talk you through everything that you need to know for your Paper 1 Chemistry.
Right, okay, year 11. So what we're going to start with is we're going to start with spec 1. It's a natural place to start. So for spec 1, and the first thing that we're going to start with is atoms. So what I'm going to do is I'm going to draw an image of an atom, and then I'm going to fully label it. So I'm going to use helium as an example, and I'll show you why in a second. So inside helium, this is what you would have on your periodic table. So you'd have the symbol for helium, you would have a top number of 4 and a bottom number of 2. So when it comes to drawing atoms, what we'd need to do is think about the number of protons. Now, we know that the bottom number on the periodic table tells us the number of protons, and therefore I've drawn 2 protons in the nucleus, and I'll fully label this in a second. The top number tells us the protons plus neutrons, and that is called the mass number. There we go, make sure it's still in focus. So the next thing that we're going to draw into this diagram, so here we've got the nucleus of the atom. The next thing I'm going to draw are the electrons. So although the bottom number is mainly there as the atomic number to tell us the number of protons, what it also does is it actually tells us the number of electrons as well. So I'm now going to draw the electrons into their shell, as it is for helium. So helium, we can see it's got 2 electrons, and we should hopefully know that the maximum for the first shell is 2. So I'm just going to put 2 X's into its first shell, and there we have it. So I'll just label each of these. So your thing there in the center are your protons. These are the neutrons in the nucleus, and these X's are the electrons. So that is a fully labelled atom. Now you're also expected to understand the masses and charges of all 3 of those subatomic particles. Now there was a question in that exam booklet that mentioned subatomic particles.
Mr. Eddy, is there any chance you could swap to a bigger pen, just so you
I
can see a little bit clearer?
I can, yeah.
A couple of people are just saying that can't quite see what you're writing with. Thank you, sir.
So subatomic particles, I'll continue.
Thank you.
So protons, neutrons, electrons, and then mass and charge. So the mass of a proton is 1, the mass of a neutron is also 1, and the mass of an electron, in the exam, you are allowed to write 0. The mass of the charge, of a proton is +1. The charge of a neutron is 0 because it is neutral, and the charge of an electron is -1. So that is your fully labelled diagram of an atom, and also the mass and charges there. Now, the next thing we're going to look at is compounds, and then briefly chemical equations. So, for example, a compound. So the definition of a compound is 2 or more elements chemically bonded. So an example would be, let's say, sodium hydroxide. So we've got sodium in there, there is oxygen, and there is also hydrogen as well. So 3 elements all bonded together. If we put that into a chemical equation, so we'll have, let's have ammonia. So we've got nitrogen plus hydrogen produces NH3. Now, in terms of balancing equations, what we need to do is firstly look at either side of the arrow. So just looking at this side, we've got 2 nitrogens there, 2 hydrogens that side. Right side of the arrow, we've got 1 nitrogen and 3 hydrogens. So to balance it, the first thing we need to do is balance up our nitrogen. So we put a 2 in front of that. That now means that we can change to a 2. Hydrogens, however, we now have 6 of them because we multiply this number by the little number next to hydrogen, which gives us 6. So then we go back to the other side of the arrow to change the hydrogen. What do we multiply by to get to 6? Must be a 3, and therefore it is all balanced. So that is compounds and chemical equations. Now, in terms of definitions of elements and mixtures as well, I'll write that on before I change sheet. So elements are atoms with the same number of protons. Mixtures are 2 or more elements or compounds not chemically bonded. So, first part of spec 1, you've got your atom fully labelled. You've got your masses and your charges for each of these. Key point from that are the subatomic particles there. When it says subatomic particle in your exam, what it's referring to are protons, neutrons, and electrons. You've got a definition for elements, compounds, and mixtures there, and also just a simple example of a balanced equation. What I'm going to do now is I'm going to go on to separation techniques. I'm going to go on to separation techniques and just run you through how we separate things. So still on spec 1. So, list of separation techniques. Are as follows. So we've got filtration, which is separating undissolved substances from a liquid. You've got evaporation. This is for separating dissolved substances from a liquid, and that is using heat. You can also separate dissolved substances from a liquid using crystallization. It's the same thing, however, evaporation uses heat. So, for example, that would be involving a Bunsen burner. Crystallization would be the same thing, except you just leave it on the side and allow the liquid to evaporate of its own accord. So you've got chromatography. The other two would then be 2 forms of distillation. So you've got distillation, and then also, I'll write it over here, fractional distillation. Chromatography is for separating a mixture of liquids. And distillation is for separating liquids with different boiling points. But BP, so that stands for boiling point. So there are your separation techniques. What we're going to run over now is the history of the atom. So very briefly, so history of the atom. and there are some key figures that you need to know for this. So the first one is Thomson, and he proposed the plum pudding model. Which looks like this. So you've got a big ball of positive charge with randomly placed electrons, like the plum in a plum pudding, hence it being called plum pudding model. Next guy who came along was Rutherford, and he did an experiment. I'll draw that one over here, I think. And Rutherford used the plum pudding model, and he wanted to test it using a gold foil experiment. So what he did is he got a piece of gold foil and he fired alpha particles at it. Now, I was expecting them to bounce back, really, because he thought this was a physical thing, it was just going to bounce back. However, what actually happened was some of the particles firstly went through, and a lot of them scattered to the side, and the odd one actually bounced back. And what that proved was that firstly, in the atom is made up of lots of space. But also that it had something at the centre which was positively charged. Two more scientists that you need to be aware of. Niels Bohr, who discovered or categorized electrons into shells. And Chadwick, who was credited for discovery of neutrons. Okay, so that is the history of the atom. A couple more things from me before we move on to Spec 2. So, electronic structure. So, maximums for each shell before we pick an example. So, the maximums for each shell. So, it's called the octet rule, and it is the first shell can have a maximum of 2, second shell a maximum of 8, and the third shell can also have a maximum of 8. So if I pick, let's pick magnesium as an example. So magnesium, the top number for magnesium is 24, bottom number for magnesium is 12. So we can ignore that when we're looking at electrons because it's the bottom number we need to look at. So if we're drawing this, if we're writing it out to start with for numbers, we know it's got at least 2 in the first shell, so it'll be 2. We've then got 10 left over, so it's got to be 8 in that second shell, and therefore in the final shell we've got 2. So if we then can draw that as a diagram, we'd put 2 in the first shell, 8 in the second shell, and then the third shell, as we've written above, will have 2. So that is how you draw the electronic structure. Key point around this, if you use the group numbers on your periodic table, so group numbers tell you how many electrons are in the outer shell. So that's electronic structure. I think sticking with groups. So there are 3 groups that you need to be aware of for the exam. So these are group 1, group 7, and group 0.
Mr. Johnny, quick question.
Yep.
Do we not need to know past 288 for an electronic structure?
Say that again.
So for electronic structure, do you need to know past the third shell? So it's 288.
No.
So just
So you need to know 288. The maximum, you need to know the first 20 elements. So you need to know up to calcium. So the highest that you'd be possibly asked would be 2882. So you wouldn't have to need, you wouldn't need to know past that. So as long as you know 288, potassium and calcium is going to be 2881 or 2882, and that would be absolute maximum you'd need to know. So for these three groups, the trend for group 1 is you go down the group, they get more reactive. The trend in group 7 is down the group, they get less reactive. We'll come on to why for both in a second. And group 0, they're unreactive. And the reason for that is because they have a full outer shell of electrons, and therefore the word we use to describe them is stable. So going back to group 1, as we said, going down the group they get more reactive, and the reason for that is all to do with the distance between the nucleus, which is positively charged, and the electrons on the outside. So if this was lithium, the distance is quite small. However, by the time you get down to potassium, the distance is much further, so therefore it's much harder for potassium to hold on to that outer shell electron, so it loses it very easily. It's the exact opposite for group 7. So for fluorine, the distance between the protons and the outer shell electrons is very close, so it's very easy for it to grab an extra electron, whereas by the time you get down to, let's say, bromine as an example, the distance is much further, so it's harder for bromine to grab in an extra electron. So final thing from me for spec 1 is periodic table. So for periodic table, you need to remember this guy, Mendeleev, and he arranged them in 2 ways. Mass and also reactivity. So he looked at the type of reactions that these elements might be put into, and if they had similar reactivity, he put them into the same group. He also ordered it in mass. Key point about Mendeleev is he left some gaps, which was really important. So he left some gaps, and that then showed that there were some other elements still to find. So what I'll do is I'll pass you over to Mr. Klee, and he's going to talk you through spec 2.
Oh, hello everybody. Right, I'm going to start with ions. So ions, to start with, relies on your knowledge of the atom. So if we start by looking at the periodic table, because this is absolutely key when we need to learn about bonding. So the first thing to look at when we do bonding is, on your periodic table, when you walk into your exam, you want to do a stepped line along your periodic table like this. This helps you to separate the non-metals and the metals. And that's really important because that tells you the type of bonding that you're going to be, that you're going to have to do. So the first one I want to look at is ions. So if we start with sodium. So sodium has a proton number of 11, which means it has 11 electrons in 3 shells. 2 in the first shell, 8 in the second, and then 1 in its outer shell up here. At the same time, I'm going to do chlorine. Now, chlorine has an atomic number of 17, which means it has 17 electrons. Again, in 3 shells. Now, you notice that I'm doing the electrons from sodium, I draw them as circles, and the ones from chlorine I've drawn as crosses. This is the reason why it's called the dot and cross diagram. These electrons are no different to each other. It just allows me to show the difference in a diagram really easily. Now, When these two materials react together, they react, and it involves something called electron transfer, and that's really important in ionic bonding. And that transfer literally means that the electron goes from one to another, and the aim is to get a full outer shell. Both these elements want to be like the group 0 elements, like Mr. Addy said. They've already got full outer shells, and that's the aim of these elements here. So this electron in sodium will leave and move into that space in the chlorine, into the chlorine's outer shell. What that does to sodium is it gives it a full outer shell. Now, because it's got a full outer shell, we have to draw this differently, because if we didn't draw it differently, it'd be like we were drawing neon. So in order to show it's different, we put square brackets around it, and we also give it a charge. Now, because this has lost a negative, it's become less negative, therefore it's become positive. At the same time, chlorine here has gained an electron. Now, because it's gained an electron, it's become more negative. Sorry, I should have drawn that to show that it's come from somewhere else. So it is now negatively charged. Now, the reason that the periodic table is important is because sodium here is a metal. Chlorine here is a non-metal. And if we have something that's a metal and something that's non-metal, then we always have ionic bonding. The next type of bonding that I want to look at is covalent bonding. Now, covalent bonding relies on two things. In covalent bonding, you have to just have non-metals. So metals do not make covalent bonds. And also, the group number of the non-metal is really, really important because it's all about spaces in outer shells. The number of spaces tells me the number of bonds different elements can make. So the number of spaces in their outer shell equals the number of bonds. So for example, carbon makes 4 bonds, nitrogen makes 3 bonds, oxygen makes 2 bonds, fluorine, chlorine, hydrogen, bromine, things like that, all make 1 bond. And that's really important when we come to determining structure. So I'm going to take an example of carbon dioxide. Now we'll do ammonia first. So ammonia contains nitrogen and hydrogen. The formula for ammonia is NH3. Now, when I do covalent bonds, what I do first is I figure out what the displayed formula is. So I know that nitrogen can make 3 bonds, hydrogen can make 1 bond each. What that means really is that nitrogen bonds separately to 3 separate hydrogen atoms. And then in covalent bonding, the thing you have to remember is covalent bonding involves shared electrons. So the atoms bond together because they are sharing electrons, which joins them together. So nitrogen here will have an overlapping shell with a hydrogen there and a hydrogen there. Now this structure here, this displayed formula, literally means, that bond means that they are sharing electrons. They are sharing 1 electron from the hydrogen, which represent the crosses, and 1 electron from nitrogen, which represents circles. So I can put them into my bond down here. Now the tricky thing about this diagram, and the thing that trips people up, is you have to remember that hydrogen's only got 1 electron shell, so it's only got 2 spaces. So those shells, because it's now got 2 electrons, they're now full. The nitrogen, however, started with 5 in its outer shell. Just to remind you from the periodic table, nitrogen's there. So I need to put in 2 electrons from the nitrogen, which gives me full outer shell for nitrogen. I can check that because I can go around and I can count to 8. 1, 2, 3, 4, 5, 6, 7, 8. Just to show you one more example, if we do CO2, carbon makes 4 bonds and oxygen makes 2 bonds each. So in order to bond carbon to oxygens, I need to have 2 bonds. So we have double bonding going on here. Double bonding means 4 electrons because there must always be an even number of electrons in the overlapping part, in the overlapping section of a covalent bond. So, 4 double bond means 4 electrons. 2 from carbon, 2 from oxygen on both sides. So the first thing that I always do is I will always draw the carbon and the oxygen with the overlapping bonds, put the electrons in that I know are overlapping because I've got sorry, lost my train of thought there. So I've got 2 electrons and from each, which makes that full outer shell here. Now if I look at the carbon, now the carbon has now got 8 electrons because it can use and share the oxygen's atom electrons. The oxygen has 4 more electrons, which it brought along because it had 6 electrons to start with, and this one here also has 6 electrons. So that's covalent bonding. The third type of bonding, and I think the final type of bonding that you need to be aware of, is metallic bonding. Now, metallic bonding is much more straightforward because metallic bonding will look the same however you do, however you have to draw a metallic bond. So metallic bonds are made up of positive metal ions. So metals have free electrons. So because metals have free electrons, what happens is that we have a situation where the electrons actually disassociate from the outer shells of the metals that brought them into the bond. So normally, if you had a lot of positive metal ions, these positive metal ions would push each other apart because they are the force between them would repel. But because of the electron that were brought into the situation, we have a substance that acts almost like a movable glue. So the electrons stick the positive metal ions together. This is really important because these electrons can actually move, and they are delocalized or free electrons, which, as I say, they act like a movable glue, sticking the positive metal ions together, but also able to move through the material. Okay, and these are the positive metal ions. So as I said, relating that back to the periodic table, if you've got something that's just metals, metallic bonding, just something that's just non-metals, covalent bonding, and one of each is ionic. Now moving on to ionic compounds. Sorry, I've got some, here's one I prepared earlier situation. This is an ionic compound. So this is called a giant ionic lattice. Okay. Now, the giant ionic lattice that you can see here is made up of positive lithium and negative chlorine, and it is held together by an electrostatic attraction. Now, electrostatic attraction is the same attraction that you feel when you put a balloon and you rub it on your hair and it makes your hair stand up on end. It's basically the force of attraction between the positive and the negative ion. Now, there are 3 types of giant ionic lattice diagrams that you might have to look at. You might have to look at a 2D one, you might have to look at a 3D space fill, and a 3D ball and stick. This 3D ball and stick model is really useful because it allows us to see that each lithium ion is bonded to 6 others in 3 planes. Okay? However, it doesn't give us a true representation, and the ball and the space fill does. So the key thing about ionic compounds is that they are made of charged particles. They're bonded by electrostatic interaction, and those ions cannot move. So because that is a really, really strong bond, what we have is substances with a high melting point. They also have a high boiling point. They are very, very strong substances. And they do not conduct electricity when solid. However, they do conduct when these ions are free to move. And they are free to move when this material is either aqueous, which means dissolved in water, or the alternative is we melt them. Okay, so that's ionic compounds. The other type of compound that we've got here, this is a giant covalent structure. So I'll come back and look at some specific examples of this in a minute, but this is basically silicon dioxide. Now, silicon dioxide is sand, effectively. It's a very, very strong material. It's a very, very hard material. If you look at this, it's got lots and lots and lots and lots and lots of covalent bonds. That means it needs lots of energy to break those covalent bonds. And because it needs lots of energy to break the covalent bonds, it also has a very, very high melting point. I'll come back and look at something similar to that in a second. Okay. As I said, here are the next thing I want to look at. So these are different types. These are allotropes of carbon. Now, allotrope means that these are different forms of carbon, but in the same physical state. So they are both solids. This here is diamond, and this here is graphite. Now, the most important thing about diamond, and the thing that leads to the structure, is that diamond is bonded, each atom, like this one here, is bonded to 4 other atoms. However, graphite comes in sheets, so each carbon atom is only bonded to 3 other carbon atoms. And that's effectively what leads to the difference in the properties between diamond and graphite. You should know that diamond is very hard. It's got very, very high melting point because of all the covalent bonds that would need to be broken to melt it. It's non-conductive. And it also, basically, light can pass through it. It's got a very, very high refractive index, and that's the reason why it's so shiny and so sparkly. But the key thing that we use it for is because of its hardness and its high melting point. So it's used for things like drill tips. The reason it's not conductive is because it has no free electrons. And this is the reason why graphite does conduct, because graphite has free electrons. Just like the metallic bond, which we have here, which has the delocalized free electrons, graphite and its free electrons means that it can carry current or electricity through the material. Okay? Also, these dotted lines here, they represent intermolecular forces, and these forces are weak. So because we've got these weak intermolecular forces, these layers can literally slide past each other. So you probably know that pencil lead is actually graphite. And when you rub a pencil on a piece of paper, sorry, my spelling's awful there. When you rub a pencil on a piece of paper, layers of graphite are being left on the paper. Okay. So, as I said, free electrons carry electricity, and that's the absolutely most essential part of this. A couple more areas of this topic. The next thing I wanted to look at, leading on from that, are 2 different allotropes of carbon. This one here, this is called graphene. Now, graphene is a relatively new invention. Graphene is a substance that's used. Graphene is a substance that's used for touch screens and things like that. Now, effectively, what this graphene sheet is lots and lots of sheets of graphite that have been stuck together. So this structure here is lots of those structures just stuck together in a repeating way. So graphene has a lot of similar properties to graphite. So it still has free electrons, delocalized electrons. So it still conducts electricity. However, because now we only have one layer, as opposed to many layers, this is now transparent. And because these atoms are all joined together in one big sheet, rather than in small sheets that can slip away from each other, this is now a very strong yet flexible material. So this is absolutely ideal for stuff like touchscreens on mobile phones. If you've ever broken the glass on your mobile phone, you'll realize that the glass touchscreen keeps working. And that's because the graphene, which is a transparent layer on top of your mobile phone, does not break because it is so strong. If you've really broken your phone, you might actually have seen how flexible it is. And it's the fact that it conducts electricity that allows it to figure out where your finger is on the screen and to work effectively as a touchscreen. The other final allotrope of carbon is a buckyball, or to give it its Sunday best name, is a Buckminster fullerene. And the structure of these is very much like an old school football. And the reason these are so useful is because they can be used as a molecular cage, and you can put things inside the buckyball. So for example, one avenue that we think about using these things is for a drug delivery system. So a classic example would be a chemotherapy drug. So a chemotherapy drug, chemotherapy is a really strong treatment that's used to treat people with cancer, and it has nasty effects all over the body. If you were able to put and cage a chemotherapy drug inside something like this, you would be able to deliver it to the part of the body where it was needed, rather than to let basically just inject it into the whole body, and we could reduce the systemic effects. Okay, right, I'm just going to come back to the metallic bond, because there is the metallic bond, as I said, the free delocalized electrons can be used to explain why these conduct electricity. But they can also be used to explain a number of other things. The fact that these metal ions are not fixed in any positions means that we can move them backwards and forwards. And because we can move them backwards and forwards, metals end up being malleable, which means that we can bend them to the shapes that we want them to be in. It also means that pure metals are quite soft. And we have a need for metals to be hard in some instances. So scientists and metallurgists have developed another type of metal, another type of material, which is called an alloy. So alloys are mixtures of two or more metals. And by mixing atoms or ions of two different types, of different sizes, what you can do is you can stop the layers of metal ions being able to move backwards and forwards. So in this situation where we've got two different types, the large ones and the small ones, these are not in layers anymore. In the metallic bond here, these are a very even layered structure. These ions move backwards and forwards. In this one, they are much more fixed in place. This makes this material, the alloy, much harder than the original metal. A really good example of that would be something like brass. Brass is much harder than the constituent metals that it's made out of. Brass is made of copper, which is very, very soft, which we can bend backwards and forwards in wires, and it's also made of tin. But brass itself is a very, very, very hard material. Okay, I think that's almost Spec 2 finished. The only thing that's left to do is states of matter, changing state, and simple molecular substances. So if we look very quickly at changes of state, we have the three changes of state: solid, liquid, and gas. Solids can turn to liquids through melting. Liquids turn to solids through freezing or solidification. Liquids turn to gas by evaporation, and the reverse is condensation. And you can change solids into gases, that's called sublimation. And the reverse is deposition. Now, you might have to interpret data on this, so the key thing to ask yourself is if it's got a melting point of minus 260 and a boiling point of minus 170, think about it on a number line. If it's below that, it's a solid. If it's between those two numbers, it's a liquid. If it's above this number, then it's a gas. The only thing to say about simple molecular substances, I'll be very, very quick on this one, is to say that simple molecular substances are small molecules. So things like CO2, O2, SO2, NO2. And because they are small molecules, they have weak intermolecular forces and are therefore usually gases. That's pretty much all there is to say about that. Okay. I'm going to hand back to Mr. Addy now, who's going to go through some Spec 3 stuff with you.
We're just going to have a few minutes break, guys, to get some more things together. So we'll play you a song that we shall not get blocked for, so non-copyright material. Just going to have a little break.
I didn't cover isotopes. I didn't do metals. But for their reason. But I can easily. You're listening to the smooth sounds of Spec 3. So for Spec 3, it's all about calculations. So for calculations, you need to be using the top numbers, and that is all involved in calculating the MR. So what I'm going to do is I'm going to calculate the MR for 3 examples, typical examples that you might find. And I've got my periodic table with me, because I'm only human. So chlorine, top number is 35.5. So for chlorine, all I need to do, because there's a little 2 there, I have to times that 35.5 by 2, and therefore that would give me a total of 71. For something like this, you can see that there's the 3 elements involved, so the sodium, oxygen and hydrogen. So it's a case of adding all 3 top numbers together, and that will then produce the MR. Now, key point around MR, sometimes it's called relative formula mass. So you might have heard of it as relative formula mass, but it's also MR as well. They tend to write both in the exams, to be fair. So sodium's top number is 23, oxygen's top number is 16, and hydrogen's top number is 1. So when we add it all together, you get a grand total of 40. And then for calcium hydroxide, this is slightly trickier because you've got some brackets involved. Now, the little number next to the brackets is the number you're going to multiply, or you use that number to multiply by. So firstly, we've got 1 calcium. Top number for calcium is 40. Inside the brackets, we've got 1 oxygen and 1 hydrogen. So if we add those together first, we've got 16 plus 1. I would add them together first to get 17 and then multiply 17 by 2. So we'd get 34 and then add that to 40. So there we go. So that is what you would do for that one. Now, down here in the bottom corner, I've pre-written out Mohs triangle to try and to bosh this out a bit quicker. So you've got mass at the top of your triangle, and then you've got the MR multiplied by moles. If you remember, mass of Mr. Mole, then you can't go wrong, because then that will get it in the correct order. And remember, mass is measured in grams. A typical question I've written at the top here, and there's a few steps to it. It's a reacting masses question. So where you utilise your moles triangle using some information. Now it looks tricky and it's dead easy. So it says there's 10 grams of calcium. So I would write 10 grams underneath calcium because that's what the question's referring to. And then what we then need to do is use our moles triangle. So as you can see, we've got 10 grams, which is our mass, and we're going to divide that by the MR of calcium. So the top number of calcium, as we know, is 40. There's 2 of them, so we multiply it by 2 to get 80. So we do 10 divided by 80, you get 0.125. What we've just calculated there are our moles. So we can write that down now. So we've got 0.125 moles. So we're halfway there. You'd get a mark for doing that and a mark for doing that. The question's asking us about calcium oxide. So now what we need to do is look at calcium oxide, which is over here. So we know that we've got 40. The top number for calcium is 40. The top number for oxygen is 16. If we add them together, we get 56. You'll notice there's a big number in front of it, so we multiply everything by 2. So we do 56 times 2 to get 112. And then, very simply, we multiply those two numbers together and we get 14. So the last step would be 0.125 times 112 to get 14 grams. So that would be a 4-mark question. Another type of question that we might get asked is a limiting reactants question. And I've written an example at the bottom. So it says 69 grams of sodium was added to 355 grams of chlorine, and there's a little chemical equation for you there. So the first thing you need to do is work out the moles of sodium. So you do 69, because that is the mass. And we're going to divide that by 46. The top number for sodium is 23, but there's 2 of them, so we're going to divide it by 46. That gives us 1.5 moles. Over here, we're going to look at chlorine. So it tells us the mass is 355, and we're going to divide that by the MR of chlorine. So the top number again for chlorine is 35.5. There's 2 of them, so we multiply it by 2, so we get 71. If you do that divided by that, we get 5 moles. The whole point of doing a limiting reactant, the whole point of what is limiting reactant, as you can see, there is less sodium than there are moles of chlorine. So therefore, the limiting reactant is sodium. The one in excess would be chlorine. It's in excess because there's more of it. So that is MR, which is all about top numbers and adding them together. The moles triangle, reacting masses, which is the most likely use of the moles triangle, and also reacting masses. Next topic that we're going to look at is concentration, and I'm going to hand you back over to Mr. Clee to do spec 4. So firstly, we've got the concentration triangle. So this is the concentration triangle. So for this exam, there are 2 triangles to learn, not like physics. So concentration triangle. At the top this time, you've got moles, and that's divided by either concentration or volume. So here's a typical question. It says, what is the concentration of a solution with 2 moles of salt in 500 centimetres cubed? So, as you can see, the volume in our triangle is in decimeters cubed. Now, first thing we need to do is convert centimeters cubed to decimeters cubed. Now, there are 1,000 centimeters cubed in 1 decimeter cubed. So therefore, if we've got 1,000, we must have 0.5 decimeters cubed, mustn't we? So that would be our first step. So if you did that, you get yourself a mark. Next step is to follow the triangle. So you can see we've got 2 moles. So we're going to do 2 divided by our volume, which we've now got as 0.5. So we do 2 divided by 0.5 and we'll get 4, and that is now our concentration. So that will be in moles per decimeter cubed. Key point for this, you need to remember to convert your volumes to decimeters cubed. These questions sometimes look on paper because you've got moles and you've got centimeters cubed and you've got to remember this stuff, but actually it's dead easy. Convert your volume first to decimeters cubed. Once you've done that, it's either a divide or a timesing job, which is nice and straightforward. And that is pretty much it for spec 3. So you've got MR, you've got moles triangle, reacting masses and limiting reactants, and finally the concentration triangle. But if you remember the moles triangle and the concentration triangle, then it will be nice and straightforward. So what I'm going to do is I'm going to hand you back over for spec 4 to Ms. Lee. Interchange.
Okay, so the first thing that I need to look at here, first thing on spec 4, is acids and bases. So acids are chemicals that contain H plus ions, and it's the H plus ion that makes something acidic. A base is something that neutralizes an acid, and bases include alkalis that you've all heard of, okay? Alkalis contain OH ions. Now, when we get hydrogen ions and we react them with OH ions that come from our alkali, we get water, H2O. That H and that H, there are 2 H's, and that O is this one here. And that's where the H2O comes from. So there are 4 different reactions of acids that you need to be aware of, and they all make slightly different things. So the most simple one of these is when you react a metal with an acid. So, for example, you will have done this, and you will have definitely done this probably with magnesium, and when you put that magnesium into the acid, you make hydrogen gas. You also make a metal salt. The metal salt is consistent all the way through. Whenever you react one of these compounds with an acid, you always make a metal salt. And there's a really strong link there to one of the required practicals that we went through today, which is about how you extract and dry that metal salt. That was all the filtration and the evaporation. The next reaction is metal oxides. Now, when you have a metal oxide reacting with an acid, the only difference is in the product that you get at the end. So because you've got oxygen to start with, that oxygen combines with the hydrogen to make water. The third one is metal hydroxide, which are usually alkalis. Now, those alkalis, again, when they react with acid, they form metal salts and also water. This is your standard neutralization equation, but all of these will neutralize acid. The final one, and probably the most complicated one, is the metal carbonate. Now, metal carbonates are more complex chemicals. So, for example, calcium carbonate here. So it's also got a C and 3 O's. So the way that they combine themselves is we get the water, which we would have got if we had just an oxide. But because we've got a C and 2 O's as well, we also get carbon dioxide. And that is the 4th reaction that you need to be aware of involving acids. The next thing I want to look at in spec 4 is the reactivity series. Now, notice one of the comments earlier asked, do you need to know all of the reactivity series? The key thing is that you need to know these 8 metals, but there are a couple of other things that we want to slip in as well. Firstly, you should know that potassium, sodium, and lithium are in group 1. They are the most reactive metals in the reactivity series, and they are here, potassium, sodium, and lithium. The next 2 in the reactivity series that you need to know are calcium and magnesium, which are in group 2. There are a couple of others, like aluminium, but where we're going next is into the transition metals, zinc, iron, and copper. So those are the only 8 that you need to be aware of, and it is most likely that you will be asked to interpret information about reactions, maybe temperature change data or something like that. The other 2 things that you need to be aware of is the position of carbon in the reactivity series, and also the position of hydrogen. Okay, so you need to know where hydrogen is in relation to these different metals, because when we come on to electrolysis and reduction, that becomes more relevant. So I'm just going to go on to how we separate metals from metal oxides. So the thing I want to look at here, when we separate metals from metal oxides, that means that we will have something like, for example, copper oxide. Okay? That is a metal oxide because it's a metal attached to oxygen. And we want to end up with just the metal. So we want to reduce it. When copper oxide turns into copper, it becomes reduced. The reason it is reduced is because it has oxygen taken off it. You should recall that there are 2 types of reaction called redox reactions, which are reduction, which is the removal of oxygen. And we also have oxidation, which is the addition of oxygen. And these 2 things happen at the same time. They happen in pairs. So what we need to do is we need to use a chemical to take the oxygen off copper oxide. And that's where carbon comes in, because carbon is more reactive than copper. And because carbon is more reactive than copper, the carbon can steal the oxygen from the copper. This is a type of displacement reaction. And when that happens, we end up with carbon monoxide or carbon dioxide. But the important thing is that we have reduced the copper oxide and we have just left copper on its own. Okay? And this is how we separate a metal from a metal oxide. And the key thing here is what we've done is that we've taken the oxygen off this and we've put it onto the carbon. So the carbon has been oxidized and the copper has been reduced. Now you might also be aware that there are different types of redox reactions, because there are also redox reactions involving electrons. And that is where half equations come in. So if I stick with this example that I've just used here, copper, when it's attached to copper oxide, is actually an ion. It's a copper 2+ ion. And when it's finished reacting, copper ends up on its own over here as a copper atom. Now, when that copper ion turns into a copper atom, it has to go from being positive to having no charge. So we need to make that more negative. So we have to add some electrons to it. And because this symbol here is a plus, this symbol here is also a plus. And because the charge there is 2, we have to add 2 electrons in order to make that copper. That is a half equation, and we also, and you could also, be asked to identify, in this situation here, is that copper being oxidized or reduced? And it's really difficult because there is no oxygen visible. So we use the acronym oil rig. Okay. Oxidation is loss of electrons, and reduction is gain of electrons. So all I need to do there to identify whether or not this is oxidation or reduction is I need to look at that little sign. If it's a plus, then it's being reduced, and if it's a minus, then it's being oxidized. Another example of that might be, if we look at the carbon's a bad example there, but if I look at another example, which might be a displacement reaction. So I do have a displacement reaction here. This is copper oxide reacting with magnesium. Now we know from looking at the reactivity series earlier on that magnesium is more reactive than copper. So the magnesium can displace that copper. And when that happens, we end up with magnesium oxide, and we also end up with copper on its own. Now, the half equation there for the copper is exactly the same as the one that we've just seen. We have Cu2+, it gains 2 electrons, it becomes copper. But if we look at the magnesium, that's slightly different. So this time we start with a magnesium atom, and we end up over here with magnesium joined to oxygen, so we end up with magnesium ion, which is a magnesium 2+. Now this has to become more positive, and the only thing we can use to make it more positive is electrons. So we have to decide whether or not we're going to add electrons or take them away. Now, if we were to add something that was negative, we would make this more negative, so we need to take those electrons away. And we need to take 2 electrons away. So if I use the acronym again and look at the sign, I've got a negative sign, so this must be being oxidized because oxidation is the loss of electrons. The only other thing I want to look at in this topic is I want to look at electrolysis. Now, there are two types of electrolysis, and there are 2 types of diagrams that you could be asked to look at. The most simple one is molten electrolysis. Now, electrolysis always involves ionic compounds. And as I said earlier in the Spec 2 stuff, ionic compounds conduct electricity when the ions are free to move. So when the substance is either molten, which means melted, or when they are aqueous, which means they are dissolved in water. Now, classically, we talk about, with molten electrolysis, we talk about aluminium oxide. Now, the formula for aluminium oxide is Al2O3, and it is made out of 2 ions, and the 2 ions it is made out of is aluminium and oxygen. And there are certain things that you need to be able to label on a diagram like this. And you'll notice already that the negative electrode is already labeled, and that is a cathode. You need to know that the negative electrode is a cathode. The other electrode is called the anode, and it is a positive electrode. And there are 3 other things that you need to be able to label on here. Firstly, you need to be able to label the liquid that's being electrolyzed, and that is the electrolyte. And that's just the fluid that contains the ions. And then we need to be able to label the positive ion and the negative ion. Now, the positive ion, in this case, is aluminium, and the negative ion, in this case, is oxygen. Now, the positive ion will be attracted to the negative electrode and will be attracted to the cathode. Now, because it is attracted to the cathode, we call it the cation. The negative ion will be attracted to the anode, and that is called the anion. Now, molten electrolysis is fairly straightforward. You might have to do half equations as well. If you have to do half equations, again, you need to think about whether or not you are making something more or less positive. Aluminium here, which is positive, in order to make it neutral, we make it more negative, so it gains 3 electrons. Using my acronym, I can see that that is being reduced. Moving over here, I'm going to now look at aqueous electrolysis. Now, the exact same labels that I added to this diagram, I can add to this diagram here. So firstly, the positive electrode. Now, if you draw these in your exam, you will get credit for showing that you understand and can label an electrolysis diagram. You will get credit for showing that you know the positive ion is called the cation, the negative ion is called the anion. So the positive electrode, as we already said, is called the anode. The negative one, the cathode. The positive ions, which are labelled here, which are attracted to the cathode, they are the cations. And the negative ions, which are attracted to the anode, are the anions. just as before, the fluid, the liquid, is called the electrolyte, which I'll write down here because it's too small to fit in that box. There is one more label on this diagram, and that's just the cell, which is providing the power. Now, there are two rules that you need to know for aqueous electrolysis. The first rule governs the products made at the cathode. Now, the things that are attracted to the cathode are cations, are positive ions. And the reason that we have to be aware of this is because in aqueous electrolysis, as well as the thing that you are electrolysizing, you also have hydrogen ions. And the hydrogen ions will be made, hydrogen gas will be made at this negative cathode unless copper or silver are present. So it will most of the time be hydrogen unless you're being asked for something that has copper or silver in it. At the anode, which is the negative ion, it will most often be oxygen. It will be oxygen made at the anode unless chlorine is present. There are a couple of other situations, so it could be bromine or iodine, but generally speaking, it will be oxygen unless chlorine is present. So if we had something like copper chloride, then copper will be made and chlorine will be made. But if it was sodium chloride, hydrogen would be made and chlorine would be made. So it really depends on the substances that are present. That's why it's really important that you get this information sorted, because if you've got this information sorted, then you can get some credit, even if when you have a go at identifying the products, you're not 100% accurate with that. Now, I think we're moving back on to spec 5 now, which is reactions and reactions profiles, back with Mr. Addy.
So, spec 5. Very easy spec because there's not much to it. So, essentially for spec 5, there are 3 key points that you need to be aware of. And you need to be able to firstly write the definitions for exo and endothermic reactions. Spec 5 is all about energy changes. In fact, it's called energy changes. So, I'll just move this paper out of the way so it's nice and clear. So definitions, exothermic, I've given myself a little missing word activity because I like those. So exothermic energy is released, and that is into the surroundings. So the temperature of the surroundings would therefore increase. So in an exothermic reaction, energy is released into the surrounding. I'll try and stop moving my hands. Into the surroundings, and the temperature is increased. Endothermic reactions is the exact opposite of that. So energy is absorbed from the surroundings, and the temperature of the surroundings would therefore decrease. So therefore they would decrease. Now, a nice easy way of remembering this is using the beginning letters of each word. So exothermic, energy exits. Endothermic, energy enters. So if you remember that, it'll make it nice and easy. So a couple more things that you need to be aware of for this spec point. So you've got energy profile diagrams. So at the side, the y-axis on these is energy. So you've probably seen these a few times. So you've got 2 different types of reactions. So we'll do endothermic first. So this is going to start down here. So it's got very little energy. It's then going to increase up to here. So that would be endothermic. So as you can see, it starts off with very little energy, and then by the end of the reaction, it has got more energy. Therefore, it's absorbed that energy. Linking to our definition, it is an endothermic reaction. Exothermic, slightly different. So it starts off with a decent amount of energy. There's a little hump, which I'm going to explain what that is in a minute. And then it ends up with less energy. So they're your two different energy profile diagrams, or energy level diagrams. Now, there's a couple of things that you need to be able to, well, 4 things actually you need to be able to label onto these. So these are the reactants on the left-hand side. On the right-hand side, you've got products. This is higher. Whoops, I've started to write profile. Products. So they are products. And then there are 2 other things that you need to be able to label. Activation energy, which would be that amount of energy there, and that amount of energy there. So the energy change on this particular diagram would be here, and the energy change on this particular diagram would be there. So they are your 4 things that you would need to label. Final thing that I'm going to talk about are bond energies. So this is nice and easy. Now, this information at the bottom here, you would be given an equation and the bond energies, probably in the form of a table, in your exam. So as you can see, the bond energy for a nitrogen molecule, so one nitrogen atom to another one, is 945. So right there, we've got 945 for our energy. Here, you've got hydrogen. Now, hydrogen bonded to itself is worth 432. However, we've got 3 of them. So what we need to do is we need to multiply 432 by 3. The reason we do that is because we have 3 molecules. So every one of those molecules, it's worth 432. However, there are 3. That will give us a grand total of 1,296. And then on the other side of the arrow, you've got ammonia. Now, 1 nitrogen to hydrogen bond is worth 391. However, you can see we've got 3 of those in this molecule. So to start off with, this is the shape of our molecule, to give you a bit of an idea of what it looks like. So we've got 3 bonds in there. However, again, we've got a big 2. So 2 multiplied by 3 gives us 6. So we have to multiply our bond energy by 6. That gives us 2,346. That's quick maths, isn't it? So what you then need to do is, once you've worked out your bond energies, it may ask you for the total energy change for the reactants versus the products. So we have to add up everything on the left-hand side and then compare it to the right-hand side. Absolutely quick maths. So 945, we're going to add that to 1,296. That gives us a grand total of 2,241. All right, we've already got this side, so it's 2,346. So what you then need to do is you need to do reactants, so left-hand side, minus the right-hand side, which are our products. For this reaction, it gives us a total of minus 105. Now, that would probably get you 3 marks. So you get your mark for doing your left-hand side, your right-hand side, so your products, and your final answer. Now, there is a final step, and I'm just going to jot it in up here. If it's a negative number, so negative number, that's exothermic. And if it's a positive number, it is endothermic. And again, the way you work that out is you do your left side minus the right-hand side. Final thing I'm going to do for spec 5 is, I'll do it in pink because it's in my hand. So spec 5 is, if you remember this word, it's not a word, bendomex. That tells you what's happening with the bonds. So firstly, you've got the first part of that word, bendo, and then mex. So bendo stands for breaking bonds is endothermic. Making bonds is exothermic. So if you think about that, if I tried to break this pen, that would require some energy, so therefore there'd be some energy absorbed and the pen would break. That would be an endothermic reaction, breaking bonds, and therefore the opposite, making bonds, is exothermic, and that is it for spec 5. So what we're going to do, we're going to have a break now until 7:30, and then we'll be back for doing the separate picks, and there aren't many of them, so see you in a little while. Cool, I think we'll crack on with with this. So for spec 1, for the chemistry separates exam, there's 2 topics on there: transition metals and properties of metals. But actually, we can kind of fit that all onto one A4 sheet of paper. So transition metals, dead easy. I'm not going to go for pink. I used pink last time. I'll go purple. I like purple. So spec 1. So ultimately, for transition metals, which is the only chemistry separates part of spec 1, you need to be aware of certain transition metals in particular that they might throw into questions. So they sometimes throw in chromium, sometimes manganese, sometimes iron, sometimes cobalt, nickel, and copper. So they were ones that you just need to be happy with by name, and also maybe be able to locate on the periodic table in terms of symbols. So in terms of transition metals, there's only really 3 to 4 key points that you need to be aware of, and these are some properties. So if we say some properties first, so properties of transition metals, they're denser, because we're going to compare these to group 1 in a second. So they're very dense, harder, they have a higher melting point, and they are stronger, bigger, better, faster, stronger than group 1, and that is group 1 metals. My handwriting's going. So than group 1. In terms of reactivity of these transition metals compared to group 1, so reactivity compared to group 1, this is with water, oxygen, and the halogens. Now, halogens is group 7. It's another name for group 7. So the reactivity compared to group 1, they are less reactive. So if you dropped iron into water compared to, let's say, sodium, it would react far less, so they are less reactive. And a couple more things you need to be aware of are some uses. So transition metals are useful as catalysts. So I enjoyed scaring my classes doing a catalyst practical. And transition metals are one of those uses, so they're often used as catalysts, so to speed up reactions. And you also just need to be aware that transition metals form more than one type of ion in some cases. Form more than one type of ion. So that is pretty much it for, I've written transitions at the top, I just noticed. So let's actually give it its proper title, transition metals, there we go. So you've got some examples there that you just need to be aware of. You don't need to necessarily learn them, but you need to be aware of they are transition metals. They may be the ones that they put into an exam, so don't let that throw you. Some simple properties, so they're denser, harder, higher melting point and stronger than group 1. They're also less reactive than group 1. If you remember your group 1 practicals with your teachers, I'm sure they chucked lithium, sodium and potassium into water and they will have fizzed, if not set on fire, if not exploded. They can be used as catalyst transition metals, and finally they can on occasion form more than one type of ion. So what I'll do now is I'll pass you over to Mr. Clee and he's going to go through spec 2, which is essentially built around nanoparticles.
Okay, with nanoparticles here, there is a really strong link to the allotrope of carbon stuff from spec 2 that's on the trilogy content. So this here is effectively a sheet of graphene that has been rolled up to form a nanotube. So a nanoparticle or a nanotube is defined as one that's got a diameter of between 1 and 100 nanometers. Now, just to put this into scale, a nanometer, 1,000 nanometers is the same as 1 micrometer. Now, this is really small because if we divide a meter up into 1,000 pieces, they are millimeters, which is 1 times 10 to the minus 3. And then each of those millimeters can be divided up into micrometers, 1,000 of them, which is 1 times 10 to the minus 6. And then each of those micrometers can be divided up into 1,000 nanometers, which is 1 times 10 to the minus 9. So we're talking about things that are really, really, really small, between 1 times 10 to the minus 9 and 1 times 10 to the minus 7 meters across. So very, very thin. It says here, obviously, they have the same properties of graphene because we've got essentially a graphene sheet rolled up into a tube. So they can still conduct electricity. They are very, very strong, just like graphene. They are very flexible, just like graphene, and they have a very, very large surface area to volume ratio, which is absolutely key. Now, there are a couple of properties that they might ask you about, and you need to link their properties to their uses to their properties. So, for example, 2 that are most likely to ask you about are the fact that nanoparticles are used as catalysts, and that links directly to the fact that they have a large surface area. The larger the surface area, the faster a chemical reaction. The larger the surface area of a catalyst, the more effective that catalyst can be at doing its job. The other major use that I would expect to see them in is electrical circuits. Okay, we're talking micro scale electrical circuits. Okay, and that's because they conduct electricity. You might see these given about some future applications in terms of medicine, in terms of nanobots and things like that. And also because of their strength and flexibility, nanoparticles might have some other applications that you might be expected to look at. But that's essentially it when it comes to nanoparticles. It's just an extension of the stuff that we already have seen when it comes to the properties of graphene and the Buckminster fullerene. Okay, so the spec 2 additions onto that are pretty limited. Now, Mr. Addy, would you like me to go straight on to the spec 4, or do you want to do spec 3 now?
I can do, yeah, I can maybe go straight to spec
Right.
4 now. Yeah.
Okay, so I will go on to the spec 4 stuff. So the spec 4 content that is additional for the separate science is essentially twofold. The first one is titrations. So here we go. Right. So a titration is a way of calculating concentration of an unknown acid or alkali from a known one, and it relies on this equation triangle here. So the number of moles of a solute that's present in a solution is dependent on the volume of that solution and the concentration of that solution. So here we have one of the reactions, which is hydrochloric acid reacting with sodium hydroxide to form sodium chloride and water, and some example results. So you would be given one of them. So this information is given here, 25 centimeter cubed of sodium hydroxide, and this information here. So what we need to do is to plug these numbers into this this table here, and then use it to, I'll show you how to use it. Okay, so hydrochloric acid, we have a volume of 23 cm cubed. Now the first thing we need to do is to convert that into DM3. So a double number line can help us to do that. When we convert CM3 into DM3, we divide by 1,000. That gives us 0.023 DM3. And that's because the unit of concentration that we have to use is moles per DM3. So the volume of hydrochloric acid is 0.023. The concentration that's given in the question is 0.1. And our aim is to figure out what that number is that goes there. We have this number, which I can plug straight into there. And then I need to use this equation triangle twice in order to find this out. Now this information here is really important. What that tells me is that the hydrochloric acid is reacting with the sodium hydroxide in a 1-to-1 ratio, which means that when I multiply these two numbers together to get 0.0023 moles of hydrochloric acid, I also will therefore, because it's a 1-to-1 ratio, have 0.0023 moles of sodium hydroxide. In order to finally work out the concentration, I then need to use the triangle again, but to rearrange it. And this time I need to do the number of moles divided by the volume. So it's 0.025 divided by 0.0023, and that, other way around, 0.0023 divided by 0.025, and that gives me a concentration of 0.092. So the concentration of the sodium hydroxide is slightly lower than that. The other topic to look at is strong and weak acids. So hydrochloric acid is a good example of a strong acid. Hydrochloric acid is hydrogen chloride that when you put it into water, it disassociates into hydrogen ions and chloride ions. And all of this molecule splits into hydrogen ions and chloride ions. So all of the hydrogen ions are available to react. So this is described as a strong acid. An example of a weak acid would be ethanoic acid. So ethanoic acid is basically vinegar, and ethanoic acid has this formula, CH3COOH, which links across to your organic chemistry stuff. Now this also splits into hydrogen ions, and when it does that, it splits into ethanoate ions as well. Now when that happens, only about 1 in every 1,000 particles of ethanoic acid will split. So at any one time, only 1 in 1,000 of the hydrogen ions are available to react. So we describe this as being partially disassociated. I can't spell disassociated. And we would describe this one here, the strong acid, as being fully disassociated. Well, that means when we have reactions that involve strong and weak acids, the strong acid will react much faster than the weak acid. So that's the strong acid there with a very steep rate of reaction. However, the weak acid is a little bit like the tortoise. It gets there in the end and it reaches the finish. And the reason for that is because it still has the same number of hydrogen ions present. It's just they're not all available and ready to react. Okay, so vinegar is acidic, but it is, although it can be as concentrated as hydrochloric acid, it is not as strong, and therefore that is the reason why vinegar is not as dangerous an acid as hydrochloric acid. Okay. Just 1 second, guys.
Don't forget now, this is set 1 only, this is separate science. So if you're anything less than set 1 or you're from Trilogy, switch off and do some revision. This video will be going onto YouTube and upload in about half an hour's time, so you can watch it, rewind it and play it as you want. But this is set 1 stuff only, okay?
Yeah, so spec 3, there are a couple of, well, 2 or 3 equations, I suppose, that you need to be aware of for spec 3 separates. So first one is percentage atom economy. So what you need to be able to do is you need to be able to firstly find the MR of the useful product and divide that by the MR of all products. So as you can see, the question might be asking you about magnesium oxide. So it might be saying to you, what is the percentage atom economy in this reaction? The useful product is magnesium oxide, so let's take that off and use it for something. Carbon dioxide is just a waste product. So the first thing we need to do is work out the MR of this useful product, which is this one here. So we do the top number for magnesium, which is 24, and the top number for oxygen is 16. So if you add that together, we get an MR of 40. What we then need to do is divide that by the MR of all the products. So carbon dioxide, we've got 1 carbon, which is 12, and 2 oxygens, so added up, we've got 44. So we'll do 40 divided by 84, and the reason it's 84 is because we're dividing it by all the products, not just the waste products. So we get an answer of 0.48, I believe. That obviously is a decimal. We wanted a percentage, multiply it by 100, so we get 48%. So the atom economy in this reaction would be 48%. Another equation for you to be aware of is percentage yield. So this is looking at if a company's making some form of compound, and they're wanting to know what the percentage is in terms of yield against what they theoretically or predicted they were going to make. So RAM is not the same as RFM, so I've just spotted that question. So relative atomic mass is purely the top number on your periodic table. Relative formula mass is when you're adding them up for a compound. Now, just quickly at the top of here, Cl2, you can actually work out the relative formula mass for that because there's 2 of them. So you'd multiply chlorine by 2 to get 71. So that's the difference between relative atomic mass and formula mass. Atomic mass is purely the number on your periodic table. Formula mass is if there's more than 1 atom. Anyway, back to percentage yield. So the actual yield for this, in this, whatever this was, 22 grams, and we're going to divide that by our theoretical yield. So you very simply do 22 divided by 50. That gets you 0.44. I'm on fire tonight. And then we multiply that by 100, and that gets you 44%. So these are your 2 percentage equations. Another equation that you need to be aware of, and it is sort of in the form of a triangle, really. Now, gas volumes. Now, for gas volumes, 1 mole of any gas, and I've put at RTP, so room temperature and pressure, is 24 decimeters cubed. So you just need to remember the number 24 decimeters cubed for molar volume. Now, this question here says, how many moles in 72 decimeters cubed of hydrogen gas? So we're working out the moles. So we can cover up the moles. And we're wanting to know how many moles there are of 72 decimeters cubed of hydrogen gas. So our gas volume, tells us in the question, is 72. We know our molar volume, if we've remembered, is 24. So therefore, it will be 3. Pretty sure I've got that right answer. Divided it by 24. Look at that magic. So that is going to be our moles. So the last thing that we're going to do, and I've actually got a past paper question for us to attempt, is linked to concentration. Now in this lesson, you may or may not have done a titration, perhaps to get some raw figures. I'm going to go with a nice shade of purple for this one. So firstly, let's calculate the concentration of potassium hydroxide in moles per decimeter cubed. So you'll notice it tells us a volume of nitric acid, and it also tells us the number of moles. So what we need to write down is our moles triangle. Sorry, concentration triangle. So if you've got moles, and we're going to multiply that by concentration, divide that, sorry, by concentration or volume. Now remember, volume is in decimeters cubed. Just add as units on. There we go. So that's our concentration equation, sort of just tucked in the corner. So we'll use that firstly to work out the number of moles, the concentration of our nitric acid. So what we're going to do is, firstly we need to convert this volume into decimeters cubed. So we're going to do 25, as you can see, it's centimeters cubed, divided by 1,000, and that is going to get us 0.025 decimeters cubed. Now we've got that, now we've got a proper volume, what we can do is we can multiply that by 2. So if we times that by 2, because we've got a concentration here, we get 0.05. That works out our moles. So at this stage now, we've got a volume up here for potassium hydroxide. We've now got the number of moles. So as you can see, we're going to divide moles by the volume. Again, we've got the problem that this volume has sneakily been given to us in centimeters cubed. So what we're going to do is we're going to convert that into decimeters cubed. And now what we can do is nice and easy, divide our moles by our new volume, which, once I've typed it into the calculator, gives us 1.612, some other numbers. So then you just write that onto there. And I'm just going to check that against the mark scheme to check that I'm right. Look at that magic, 1.61. I'm pretty happy with that. So the next one is spec 5. There are only 2 things to know for spec 5. It's built around batteries, and it's also pen overload, and fuel cells. So firstly, for batteries, it's all about redox reactions. I'm drawing a picture of a Duracell battery and just remind you that it's a redox reaction. Now, one thing that is important in a battery is that the difference in reactivity between the 2 metals present determines the voltage. So the bigger the difference in reactivity, the higher the voltage. So most batteries you're probably seeing on TV, those rabbits that run around, powered by batteries, and they use lithium. They're lithium powered. Lithium's very reactive. They might have something like, let's say, copper in there, and it'll be in an acid, so you end up with like something like copper chloride. So if we draw a little reaction for that, this is what's going on inside the battery. So you've got lithium, let's say copper chloride, and that's then going to produce lithium chloride plus some copper. Now in that, there's actually oxidation and reduction going on, even though there isn't any oxygen present. And the reason for that is, if we write it out again, we've got some copper ions over this side, and they're bonded to the chloride ions. Lithium then turns into an ion, and then you end up with copper. So if you look here, lithium starts off with a full outer shell, and it ends up losing an electron to turn into an ion. So therefore, if you remember oil rig, that has been oxidized because it has lost an electron. Copper starts off as an ion, so it's got 2 less electrons than usual, but then by the end of the reaction, it's gained electrons again, so therefore it has been reduced. And it is these electrons, so the electrons lost, that create the electrical charge that the battery can then use to power things. So that is how a battery works. The next thing I'm going to look at is fuel cells. I'm just going to swap because it's the final colour. So we'll go with this nice shade of blue. So fuel cells, I've already started to draw out a fuel cell. So I'll do it. It's going to be the right of that weird line. So fuel cells, I've started to draw one out here. So what happens is hydrogen fuel goes in. And that will go into here. Now when hydrogen goes in, what it does is it reacts with the catalyst when it reaches the anode. So at the anode, it reacts with the catalyst. And what it then does is it turns into an H+ ion. H+ ions and electrons. So these electrons that have now been produced will go off and they'll go and power a cell somewhere. What then happens is, I'll just label this, so this is your anode. And this is your cathode. So this is your cathode. Remember, if you remember panic, so this is positively charged and the cathode is negatively charged. So the hydrogen ion, which is positively charged, makes its way over here. This is an electrolyte, by the way. I am writing sideways, so apologies if it looks a bit weird. So that's an electrolyte. The hydrogen ions make the way this way towards the cathode. So positive charged particles go through this electrolyte and the electrons travel along a circuit and they form an electrical current. And then when the particles, so these hydrogen ions and the electrons reach the cathode, so when they get over here, they react with oxygen and that forms water. So if you've, Mr. Schuller's got a Prius, does that, I think, does that work in a similar principle? Is that hydrogen powered, sir? No, it's not, is it? So, this isn't Mr. Schuller's car. So, this isn't Mr. Schuller's car. Apologies, I've misseen it.
This is space shuttles.
So when it gets to the cathode, what it does is it reacts with oxygen. So here, I'll draw this in a different colour. So you've got oxygen going in. So oxygen is just coming from the air. So oxygen's going into here. And when hydrogen gets there, it reacts with oxygen. And it produces water, and it also forms some heat. So that is fuel cells. So hydrogen goes in. What it does is it basically gets stripped of its electron, and then it makes its way to the cathode. When it gets there, it reacts with oxygen. So this is oxygen from the air. And it forms water and heat. The final thing that I'm going to write down are the half equations. So, spec 5. Fuel cells. So at the anode, you've got hydrogen gas going in. So you'd plug your car in, you get some hydrogen gas, and that loses 2 electrons and forms some H+ ions, and they're the ones that then make the way to the cathode. And at the cathode, you've got some H+ ions, some oxygen, and there's also some electrons, and that forms water. Now you notice that's not particularly balanced, so what we need to do is we need to balance our oxygen, so we stick a 2 there, which now balances that up, but we've now got 4 hydrogen, so we go back and stick 4s in front of those, and that is your fuel cell's half equations. Going back to someone asked earlier, what's the purpose of half equations? It essentially tells you what's happening at each electrode. So at this electrode, you can see hydrogen's losing 2 electrons to form hydrogen ions. Cathode, you can see that it's bonding with oxygen and also gaining some electrons back to form water, and then that comes out and that's done. So that is spec 5 finish for separates.
Okay, thank you very much, Year 11, for tuning in. We will be back on Tuesday evening to do the physics revision. We will upload this video as soon as possible. Hopefully we won't be blocked again. So we'll see. We're going to take pictures as well of all the sheets that we've used today. We're going to upload them to Twitter and Facebook. Thank you very much.
No, no.
Yeah, thank you for watching this.